Hello, my name's Thanom and I'm from UNSW. Today I'm working through some of the MATH1011 calculus problems from section 2.4 on the applications of calculus. So this is a rational function here and we're asked to sketch that rational function and we might use some calculus to determine stationary points for this graph. So first of all, if we're asked to sketch the function, we might want to work out things like the y-intercept, say, and the x-intercept. So if we're working out the y-intercept, we're substituting x equals 0. This is relatively easy. We get 3 divided by minus 1 times minus 3, or 3 divided by 3, which is 1. So when x equals 0, y equals 1. If we're trying to find the x-intercepts, we're solving y equals 0. Now when y equals 0, I need x squared plus 3 divided by this expression to be 0. If two things divide to give 0, the top's got to be 0. So when I try and solve y equals 0, I get x squared plus 3 has to be 0, which has no real solutions. So there are no x-intercepts here. So we have a y-intercept of 1, but we don't have any x-intercepts. So far I know that our function goes through 1. The other thing we might analyse are some asymptotes. So we're going to have two vertical asymptotes here. And those vertical asymptotes are going to occur at x equals 1 and at x equals 3 here. So x equals 1 and x equals 3 aren't part of our domain, but in particular here they will be vertical asymptotes. If I want a horizontal asymptote, what I'm doing is I'm looking at what my function is approaching, if anything, when x approaches infinity. Well, there will only be one horizontal asymptote. So I'm looking at the limit as x approaches infinity of this function here. So x squared plus 3 over, and I might expand this out here, x squared minus 4x plus a 3. So what does my y value look like when x is huge? Well, my trick here is to divide the numerator and denominator by the highest power of x. So if I divide everything in this expression divided by x squared, then I'll get 1 plus 3 on x squared on the numerator, and I will get 1 minus 4 on x plus 3 on x squared on the denominator. And I can see when x is large, 3 on x squared approaches 0, 4 on x approaches 0, 3 on x squared approaches 0. So this approaches 1 divided by 1, which is 1. So we have y equals 1 is a horizontal asymptote here. So let's put that on our diagram. And in fact, I might even shift this to there. So we have a horizontal asymptote at 1. That means when x is huge, y gets closer and closer to 1. So here's our horizontal asymptote at 1. It can cross through 1 in the middle. It's just saying when x is large. And in fact, it could approach minus infinity. I'll fix that up in a sec. And we also know we've got vertical asymptotes at 1 and at 3. So we'd better put those on our graph. Okay. So this was actually the limit. As x approaches plus or minus infinity, it's still going to approach 1. So stationary points are going to occur when y dash is 0. When y dash is 0. Now if we want to find y dash, we're going to need to use a quotient rule on this, which isn't so nice, but we can manage it. So if this is f and this is g, then y dash, according to the quotient rule, is f dash g minus fg dash on g squared. So f dash is 2x and g is, I might write it in expanded form, x squared minus 4x plus 3 minus f, which is x squared plus 3, g dash, well, the derivative of g is going to be 2x minus 4. So all over, I might just, so all over g squared, I might just write g squared. We're not really interested in the denominator because at the end of the day we're solving two things dividing to give 0, and we want that numerator to be 0. Okay, so let's simplify the top here. So we're going to get a 2x cubed minus an 8x squared plus a 6x. Here we're going to get a minus 2x cubed. That's a minus 4x squared, which will be a plus 4x squared. That'll be a plus 6x will turn into a minus 6x, and that will end up being plus 12. So all of this over g squared. This cleans up quite nicely. 2x cubed minus 2x cubed is nothing. 6x minus 6x is nothing. So we end up with minus 4x squared plus a 12. So that's a minus 4 outside of an x squared minus 3. All over g squared, and if you really want to write out g squared, that's x minus 1 squared, x minus 3 squared. So we can see there's no factors in common to cancel anyway. So if I want y dash to be 0, I'm going to need that numerator to be 0. So y dash will equal 0 when x squared minus 3 is 0, and so that's when x equals the square root of 3, or x equals minus the square root of 3 there. Okay, so that's when y dash is 0, when that numerator is 0. Now we want to determine whether these are maximums or minimums or horizontal points of inflection. I don't really want to differentiate this thing again, and so I'm going to look at what the sign is doing either side of each of these. So just putting these values in a table and looking at what the sign of y dash is. Well, at the square root of 3 it's 0. If I'm a little bit more than the square root of 3, then this is going to, the x squared minus 3 is going to be positive. So overall I'm going to have minus 4 times a positive number. The denominator is definitely negative, so this is going to be negative here. Whereas if I'm a little bit less than root 3, then this is going to be negative in here. So minus 4 times a negative will end up being positive. Again, I'm dividing by a positive number, so that's fine. So I know that this is going to have a positive gradient, then it's flat, and it has a negative gradient, so this is going to be a maximum here. So this is a local maximum. I don't know whether this is going to fit in the screen. Okay, whereas at minus root 3, we can see it's going to do a similar thing because it's x squared here, so similar function. So if I'm a little bit bigger than minus 3, that's equivalent to, that's kind of smaller in magnitude, so that's negative there. So this will be a positive gradient, whereas this will be a negative gradient. And so here we're going to have a local minimum at minus root 3. So what we're doing is we're looking at this expression and we're looking either side of minus root 3 or either side of root 3, and we're working out whether its gradient's y dash is positive or negative. That is the gradient positive or negative. So here the gradient's positive, and then it's stationary at root 3 and it's negative, so we've got a local max. Here the gradient's negative and then stationary and then positive, so we have a local min. Now we need to plug those into the y values. I'm running out of room here. At square root of 3, so square root of 3 is 1 and a bit, so we're in here somewhere. If we put the square root of 3 in here, we don't get something very nice, but if we put it in our calculator, we can see it's about minus 6.5. So we're down here somewhere, and we know at root 3 we've got a local maximum. So we've got some asymptotes here and a local maximum. That's around minus 6.5, and so my graph is going to look like this in that section. At minus root 3, over here. Again, if we put minus root 3 in here, we can get an expression for, or a value here. If we put that in our calculator, it's approximately a half. So we're going to have a local minimum at about minus root 3, a half here. And it's got to approach this asymptote when x approaches negative infinity. So that means it's approaching that asymptote here, but we've got a local minimum here. We have to go through this y-intercept of 1, and we have an asymptote, a vertical asymptote here. So this is my local minimum, and then it comes up through the y-intercept of 1 and approaches this asymptote here. This minimum could look better. So this is the local minimum at minus root 3, approximately a half. Here's a local maximum at root 3, and that's approximately minus 6.5 there. Now we just have to work out what's happening over here. Well, there's no stationary points or anything. We can see, if we look at the y dash, which is this expression squished in here, it's minus 4 times x squared minus 3 over something squared, which is definitely positive. Now whenever x is bigger than 3, x squared minus 3 is definitely positive here. So we're going to have minus 4 times a positive number over a positive number. That's negative overall. So we can tell that it's decreasing in this section, and this is an asymptote and this is an asymptote. So our graph is essentially going to look like this, a decreasing curve that approaches those asymptotes there. So this is our graph of x squared plus 3 over x minus 1, x minus 3. It wasn't too bad working out the intercepts and the asymptotes, but it was a bit of heavy lifting with the quotient rule and our stationary points. But we can put it all together on this graph over here.